I'm very happy to have Philipp Höhn here. He's visiting us from University College London. Philipp did his PhD at Utrecht and then did a postdoc at the Perimeter Institute where he developed his own information theoretic reconstruction of quantum theory, which is pretty impressive. And then he went on to the University of Vienna. Or did I miss something in?
No, that's right.
No, okay, yes,
well.
Okay. And then University of Vienna, and then now he's at University of College London. So today he'll be telling us about general covariance and the problem of time. So. Oh, and I should say I'm very thankful to Marcelo and ICE
So Philipp is a fellow of the Institute for Cross-Disciplinary Engagement, the one that we run here. And so he's the second one. We had this academic year. We had one that was an ethicist. And we have two others who work in completely different fields. One works in cognitive ecology, meaning is nature is plant smart at some level, and she's actually doing some pretty amazing work. And the other one is an Irish journalist / writer interested in the impact of AI and culture and society. And he wrote a book that got one of the most prestigious awards in England, called To Be a Machine, which is actually very funny. He followed a bunch of guys called transhumanists, guys that believe that they're actually transforming themselves into machines. And so he's going to be here, and so there'll be a lot of different kinds of talks. And if you subscribe to our newsletter, you know about it. Right? Sorry.
That's all right.
That's my plan.
Yeah, thank you very much for the nice introduction, and also especially for having me here. Very glad about the invitation to come here. Yeah, so in this talk, this will be a very foundational talk, the interface of the foundations of quantum mechanics and also the foundations of quantum gravity. So it has a lot to do with what happens when we take serious that reference frames are in practice always physical systems. It is something that we're kind of forced to in quantum gravity. And then one can ask questions of, how does one actually describe physics relative to reference frames that are also quantum, because as being dynamical systems, they will be subject to the laws of quantum mechanics itself, and what kind of implications that has. And in particular, what sort of, how one can switch from the perspective of one quantum reference frame to another. And in the second part of this talk, I also want to discuss a bit about how this leads to new perspectives on the so-called problem of time and quantum gravity. So since I don't really know what the background knowledge of people here is, in particular in quantum gravity, the first part of the talk will therefore be really more conceptual, and later on in the second part, I might be a bit more technical. And in any case, if you have any questions, then yeah, please shoot away. Okay, so let's get started. There's just one funny thing that I wanted to mention. So I actually wrote most of my application for this ICE fellowship in the train. That by itself is maybe not so funny, but what is funny is a funny coincidence is that I actually wrote it in a train while moving from Berlin to London, and that train is a so-called ICE train, so I guess that was kind of destined to be successful. So I should say that ICE here does not stand for Institute for Cross-Disciplinary Engagement. It's an Intercity Express, high-speed train in Germany, but anyway, yeah, so that's a bit of a background here to this application. Anyway.
This also has nothing to do with the American Immigration Service.
What is that? Is there also
the ICE office is the one that kicks all the illegal immigrants out.
Oh.
Immigration and Customs Enforcement.
I see.
Also, water in the refrigerator.
Yeah,
that's true. All right, so then let's get to the scientific part. Yeah, as the title already says, we'll deal a bit with general covariance. So let me just remind you a bit of what we usually understand under general covariance. At least colloquially speaking, we think of it usually in terms of the statement that all the laws of physics should be the same in all reference frames. So this is, of course, a pillar of general relativity, and the statement already indicates that, well, there must be some things that are independent of the reference frames, and usually we interpret this in general relativity as the laws of physics taking actually the form of tensor equations. And indeed, you can think of tensors, in fact, as being structures that are in some sense reference frame neutral. So they in some sense encode the information about what any reference frame would measure in an experiment. So I mean, if you want to know what some observer corresponding to some reference frame would measure, you can contract whatever tensor you're interested in, let's say the energy momentum tensor with some vectors, let's say, that correspond to some reference frame that spits out numbers, and these numbers would correspond in some cases to what could be measured in a reference frame. But of course, the tensor by itself is independent of a basis choice, so it encodes really, in a sense, the information about all reference frames. And now, another thing is, when we think of general covariance, of course, we in general relativity, we usually think of it also in terms of, what doesn't work, in terms of coordinate switches. So when we think of switching from the perspective of one reference frame to another, what we usually do is we assume that we have some idealized frames that are sort of painted onto space-time, in some sense external. They don't have their own dynamics, internal dynamics, I mean, or they don't back-react on space-time. So you can think of, for instance, Alice and Bob going through some spaceship through space-time. And then, well, this part of the description we can actually consider as reference frame neutral, because in order to make the statement that there are some spaceships flying through space-time, I don't actually need to specify a reference frame in order to make sense out of that statement. But if I want to say how fast they're moving, then I have to pick a reference frame. And this we can, of course, do. Usually, one way of doing it is by choosing, for instance, some vector frame and defining a coordinate system. And that defines us then a map from the frame neutral physics into some frame perspective, coordinate perspective, let's say here in this case, which we can interpret as Alice's description of the physics. Of course, we can do the same thing relative to Bob's frame. And then if we want to switch perspectives from, let's say, Alice's point of view to Bob's point of view, then, of course, we have these usual nice compositional structures of coordinate changes on a manifold, where you invert the perspective map or the coordinate map of Alice. You go back via the frame neutral physics, and then you map forward to Bob's perspective. So, of course, all of these things, but the important thing here to note is that you always, when you switch perspective from one frame to another, you always do so by actually going via some frame neutral structure in between. And the reason I'm stressing this is because this is something that we will also see in the quantum regime. Okay, so so the main, basically the whole talk will be now concerned about the question what actually happens when we take serious that reference frames are in practice always physical systems, or laboratories are physical systems, or when we use clocks to parameterize or to describe the evolution of systems in the laboratory. I mean, the clock is also, of course, a physical system. And we have rulers that may be related to the wall of the lab and so on. And as physical systems, if we at least believe in the universality of quantum theory, then, then these reference frames, they should also be subject to the laws of quantum mechanics itself. And in particular,
Before you get going to that, so do you mean the physical objects that we use to measure time and space are physical systems, but the notion of a space-time and a reference frame is not a physical system, it's a mathematical construction?
So the thing is that in general relativity, of course, we can think of reference frames in the sense of vector frames as not necessarily being physical systems in the sense that they're completely idealized, they don't have their internal dynamics and so on, so they're kind of painted onto space-time. But so this is an idealization that I want to get over with. So that's, and then I will try to argue that also in general relativity, in quantum gravity, it's kind of necessary to do so, at least in background independent quantum gravity. Yeah. So I mean, the idea in general relativity to use these idealized frames is of course perfectly fine because you're interested in the large-scale structure of space-time. And then, of course, what a small reference frame does in space-time, the back reaction is so small that for all practical purposes, when you're interested in the large-scale structure, it doesn't matter. So it's fine to neglect it. But now this here is really a more foundational approach where we really want to think of all the reference frames, such as the rocket that's flying through space-time, to be actually a physical system with internal dynamics, and that actually in the end will back react. Okay, so and in particular, if they are now quantum systems themselves, then what we will have is sort of fluctuating reference frames. And then we might want to ask, how can we actually describe the physical world from perspectives of quantum systems, of fluctuating frames. So this is something that is a question that, of course, I have not invented. This is a question that, by some historical coincidence, has emerged simultaneously in 1967, both in the foundations of quantum theory and in quantum gravity. So there was a paper by Aharonov and Susskind, and then by DeWitt in quantum gravity. Aharonov and Susskind discussed quantum reference frames, or reference frames that are actually quantum systems in the context of superselection rules. Well, in quantum gravity, DeWitt actually considered reference systems or dynamical systems really as the matter coordinate systems that through which you would actually define operationally space-time events and so on. And so despite the fact that in the same year, the recognition that reference frames should be considered also as quantum systems, that this happened in the same year, the developments in the two fields, they were actually quite different in the decades afterwards. In quantum foundations and also in quantum information, they became quite useful. There was usually an operational focus, in particular in quantum information. There's a lot of discussion about what do you do when Alice and Bob want to communicate but don't share actually a reference frame, and those kinds of things with implications for operational notions of entanglement, key distribution, and so on. While in quantum gravity, the focus has been mostly on foundational aspects. And this is something I will explain in the coming slides a bit better, what I mean by this. So one thing I want to emphasize is in the foundations of quantum theory, it turns out that quantum reference frames are very useful, but you're not necessarily forced onto it. I mean, if you believe in the universality of quantum theory, then you're kind of forced onto it. But of course, there's also people who would dispute that the universality of quantum theory holds, or there's people like Anton Zeilinger in Vienna who would argue that you would always need some classical regime in order to describe, like classical reference frames or reference systems in order to describe other quantum systems. But anyway, but the point is that I want to argue now is that in quantum gravity, and in particular in so-called background independent quantum gravity, which I will explain briefly in the coming slides, that taking serious that reference systems are dynamical systems and quantum is in a way indispensable. Okay, and this has to do again with general covariance. So general covariance understood as the invariance of the laws of physics under general coordinate transformation, so under passive diffeomorphisms. This, in fact, also implies another often underappreciated fact, namely that the theory, general relativity, is in fact also invariant under active diffeomorphisms. And of course, there's a lot of fuzz about active versus passive diffeomorphisms. People often saying they're equivalent. One has to be a bit careful with that because mathematically they're not exactly the same thing, but there can be a relation between them. But it turns out that one can argue that indeed, if a theory is generally covariant, then it must also be, in the end, invariant under active diffeomorphisms, and this actually has profound conceptual and technical implications. And I want to briefly discuss those. So what is actually an active diffeomorphism in space-time? So we may have our space-time M. An active diffeomorphism is some differentiable invertible map, a smooth map from the space-time manifold into itself. Let's say it takes some space-time event Q into some other event P in the image. Of course, we can then also reinsert Q and P on either side. And what this diffeomorphism does, it acts, for instance, when we have dynamical fields. Let's think of scalar fields, or if you want the Ricci scalar measuring the curvature, so the strength of the gravitational field, if you like. These dynamical fields will transform under active diffeomorphisms. So active diffeomorphisms will basically shift these fields around. They will move these fields, the dynamical fields, around in space-time, and they act by pullback. So what happens in this case is that suppose at the point P, originally you have some, let's say the gravitational field is curved, while at some other point Q it was flat. Then by pullback under the diffeomorphism, the field that was originally at P will be mapped to Q in the image. And so what you see here is that the value of, or the strength of the gravitational field at the space-time event Q depends on which of the representations you're in. So in one case, you have a flat, basically a zero gravitational field at the point Q. In the other case, you have some curvature there. So, since this active diffeomorphism symmetry is actually, it's a symmetry, it's a proper gauge symmetry, turns out that you should consider these two space-time situations as being equivalent. So physically they are the same. That's what's being taught by the active diffeomorphism invariance. But if we want to equate these or consider these two situations as being physically equivalent, what we have to take away from this is that, of course, a space-time event such as Q by itself doesn't have any physical meaning itself. Because in one case you have zero gravitational field there, in another case you don't have a zero gravitational field there. So this is related to, in fact, Einstein's whole argument, if you're familiar with the philosophical discussions around this. So yeah, the statement here is then, as I already said, the space-time points have a priori no physical meaning. So then you might wonder, well, what has actually physical meaning? Of course, the theory should be predictive in some sense, even as a gauge theory. So generativity is a gauge theory. And it turns out that there are, in fact, things that are predictive and that are invariant under these active diffeomorphism symmetries. And those are space-time coincidences, or in fact, relations. So you can think of, for instance, Alice and Bob, again, traveling in two spaceships through space-time. And suppose they actually, their world lines intersect at that event P. Okay, so then we could say, oh, now I'm interested in the gravitational field at the event where Alice and Bob's spaceships intersect. And it turns out that under these active diffeomorphisms, because these are also dynamical world lines, so they are subject to solving certain equations of motion, such as geodesic equations, under active diffeomorphisms, they will be also transformed, these world lines. But it turns out that they will again, in fact, intersect now at the point Q. Okay? So what you see from this argument here is that what this implies, loosely speaking, is that well, it is relations between physical systems that are, in fact, physical, that are gauge invariant, that are invariant under the symmetries of generativity. And so, in particular, when we think of localization in generativity that is invariant under the symmetries, then this localization is not done relative to the space-time background, the space-time manifold, because these different events by themselves don't have a meaning, but it's only relative to other physical systems. So you always have relations between dynamical quantities, and those are actually the physically relevant statements. Okay, so this, in fact, technically, when you want to deal with this, this leads to quite some challenges. It's conceptually also interesting, but really the message to take away here is it's generativity. The predictive part of it is really relations between physical systems. Okay. Now, this has, again, profound implications for the quantization of generativity and thereby for quantum gravity. So here we have to distinguish between quantization in space-time and quantization of space-time. So quantization in space-time, that's the usual standard way of thinking about textbook quantum mechanics or textbook quantum field theory. So there we're usually given some rigid space-time background. It may be Newtonian space with Newtonian time, where, for instance, in non-relativistic quantum mechanics, we have this T and X appearing there that we associate with a Newtonian background space. But of course, we can also do it relativistically in quantum field theory. And then, of course, one of the pillars of relativistic quantum field theory is locality, where you always say, oh, if I have now two fields, and I look at the field operators at space-like separation, then they should always, in fact, commute. That's the micro-causality condition. And yeah, so the point is here we have a rigid space-time. That's a rigid stage on which physics happens. But the matter living on it, that is dynamical and that is quantum. So now this is very different when you think of the quantization of space-time. So this is what happens in background-independent quantum gravity when you take serious this diffeomorphism symmetry of generativity. So now you cannot quantize anymore in the usual ways that we're familiar with from textbook field theory or so on, because if we take serious this background independence, then we cannot quantize space-time or gravity relative to some rigid background structure, but somehow only in a relational way relative to itself. And so in particular, when we think of a quantum state now associated to space-time or to the gravitational field, if you like, we can't think of it anymore in terms of being some wave function that depends on some background time or spatial coordinates. So thereby, we cannot expect that there's any such relation here. Yes?
Sorry, is it okay to?
Sure.
So, what about situations where gravity is weak in some sense, where you kind of have a sense that maybe you can use the usual quantization procedure?
Yeah, so what I'm talking about here is really non-perturbative gravity. So you would be speaking about perturbative quantum gravity. So it's true that when you do perturbative quantum gravity, then you can use standard textbook rules. But then you would just expand your metric around, let's say, the Minkowski metric, and then you only look at the first-order perturbations as being dynamical on the Minkowski space. Those you can quantize in the usual way, also a priori using microlocality. However, of course, as is well known, perturbative quantum gravity is not, in the end, perturbatively renormalizable. So it's not a fully predictive theory, but it's true that for weak field regimes, it is a valid, it would be a valid description. It's just here, of course, I'm trying to think of a full quantization of the full space-time with fully non-perturbative.
But given that, even in the classical description, you talk about what are proper observables, where you relate the metric to another physical system, code sequence. So that seems to suggest that even in a weak field description, if you did it properly, you'd need to have some kind of relational.
Yeah, so it's a very good point, actually. It's a very subtle point. So there has been quite some discussion about this in the last 5 years by Will Donnelly and Steve Giddings. I don't know if you're familiar with these works. So what they have looked at is indeed taking a series also, there's a gauge symmetry in perturbative quantum gravity, of course. You have sort of linearized diffeomorphisms. And then you can, of course, then you should also look for gauge invariant quantities, so also objects of the metric, or well, let's say functions of the metric, or of the metric operator in that case, that are invariant under these diffeomorphisms. And that really leads to some subtle issues. One of the things you get, in fact, is this microlocality holds for gauge dependent, or for the metric itself, let's say for the fluctuations, but only for the gauge-dependent quantities. If you look at gauge-independent quantities, you find that this no longer holds actually either. So the reason is that, of course, diffeomorphisms are very non-local symmetries. And so you will always have some global dependence on elsewhere in space-time, or even asymptotic dependence, it turns out. And then it turns out that if you really look at diffeomorphism invariant objects, they will generically not commute. They will violate this microcausality condition. And so there's a very subtle interplay there between perturbative physics in that case and diffeomorphism symmetry. It's a bit difficult, or a bit dangerous to extrapolate from this perturbative regime to the full non-perturbative regime. Yeah. So, but yeah, one could in principle discuss these things, but here, what I'm focusing on here conceptually is the full non-perturbative treatment of quantum gravity. Okay, so, or was there any other question? Okay, so yeah, I mean, as I was emphasizing, so a state of space-time can then, in this case, if you do it non-perturbatively, not depend on any background coordinates anymore. And so then you should not expect any evolution equation in the sense of a Schrödinger equation. And in fact, it so happens that in quantum gravity, and this is related to this diffeomorphism symmetry and general covariance, that your states and the dynamics should be completely independent under, it should be completely coordinate independent. And sort of heuristically, if you want to think of this, you can think of it that the only way you can have a Hamiltonian where the dynamics is completely independent on a whatever parameterization or, of the dynamics you choose is the one where H acting on the state is actually 0. So one can make this more rigorous. So this is a statement that follows really from mathematically from the structure of the theory and the symmetries of the theory, but already heuristically one can kind of understand that something like this must happen. And this goes under the name of the problem of time in quantum gravity, that now you no longer have a state evolving in some background time. That's maybe to be expected when you don't have a background, that you shouldn't evolve with respect to background. And this is often said, there's a frozen formalism. We don't have dynamics there a priori, but that's a bit misleading, because what you actually need to do again is you have to extract the dynamics from this equation from internal degrees of freedom. And this again relates back to quantum reference systems. So you basically have to choose dynamical degrees of freedom that serve in some sense as a clock degree of freedom, and then you look at how other dynamical degrees of freedom evolve with respect to that. And I hope I can discuss that a bit more later on. Now let me also emphasize here, so we were talking about this before, so if you're now in full quantum gravity non-perturbatively, then this micro-causality condition of quantum field theory doesn't make any sense. And that's because whether x and x prime are space-like, that depends on the metric, but now the metric is an operator. And so this commutation relation should be state independent, but whether x and x prime would be space-like or not would in some sense have to depend on the states. So you already see that, that such a relation like this here cannot hold in full quantum gravity. So indicating that we need to rethink the way in which we quantize space-time or the gravitational fields non-perturbatively. And yeah, so the main idea again here is that we don't do the all these notions that we're usually used to, that they're not defined with respect to some background, but that everything is relative to other dynamical degrees of freedom. And so there's a necessity in quantum gravity to actually consider quantum reference systems or quantum reference frames. Okay, so this is a very brief summary of background independent quantum gravity and why, in fact, quantum reference frames or quantum reference systems, however you want to call them, why they're actually relevant. So the upshot here is that this actually leads naturally to a relational description of physics. So as I tried to emphasize under the symmetries that come from general relativity, the physics is actually encoded in relations, so the gauge invariant physics. And so in a way you can think of it now, in usual textbook quantum theory, you have your rigid space-time and dynamical matter degrees of freedom, but now you only have dynamical degrees of freedom, both coming from your space-time degrees of freedom, the gravitational field, and the matter degrees of freedom. And now in the set of all the dynamic degrees of freedom that you have a choice that you can make of which of these degrees of freedom you would want to pick as a dynamical reference system, relative to which you evolve or describe the dynamics of the remaining degrees of freedom among the set of degrees of freedom that you're interested in, and likewise also to use some dynamic degrees of freedom as a sort of spatial reference system relative to which you localize other degrees of freedom. Okay, so in this more technically in the end leads to so-called relational observables. There's been quite some works on these over the last decades. I might, if time allows me, explain a bit more about this towards the end of the talk. But yeah, so one of the questions now I want to raise here is, okay, so suppose we have made among all the degrees of freedom that we're interested in, we have made a choice of which ones we pick as our reference system relative to which we describe the remaining physics. What actually happens when we pick a different such set of degrees of freedom, different set of reference systems among all the dynamic degrees of freedom? How does the description of physics look like relative to that choice? And in fact, how are the two different choices related? So will they in some sense see the same physics? And so that's a question I want to ask here. So it turns out that classically, when you do this with dynamical degrees of freedom, they are actually equivalent. I don't have time to discuss that here, but it's not very difficult to convince oneself of it. But in the quantum theory, this is really an open problem. And so this is also related to the so-called multiple choice problem of time. So I mentioned very briefly what the problem of time is in quantum gravity. And so as I try to stress, the way of trying to get dynamics from this a priori timeless looking equation is by choosing some dynamical degrees of freedom as serving as your dynamical clocks relative to which do you describe the evolution. And so there's been quite some discussion on this topic in the literature, especially in the 80s and 90s. And it turns out that usually when you choose different such dynamical degrees of freedom to serve as your clock, then the resulting quantum dynamics that you get, they are not necessarily unitarily equivalent. They're not necessarily related by unitaries. And so just to give you some example, in quantum cosmology, for instance, if you have two clock variables, okay, classically it's not difficult to look at how one evolves relative to another. What do you do if they're operators? That's the question here. So in quantum cosmology, if you have some really simple system like a Friedmann universe with a, let's say, a scalar field inside, a homogeneous scalar field, then you essentially have only two dynamical degrees of freedom. So these are toy models, of course. But in those cases, you could, for instance, think of the scale factor of the universe, in some sense a measure of the spatial size of the universe, as being one clock, because it's dynamical. The size of the universe changes over time in most cosmological solutions. But you could also think of, for instance, your scalar field as serving as some dynamical degree of freedom, some dynamical time standard. So you can think of it, for instance, as some inflaton field or so that evolves over the course of evolution of the universe, and that you might want to pick as your time standard. Classically, you can switch between choosing either or the other as a clock. There's no problem. But in the quantum theory, it's a different question. And so, yeah. So
these are examples of what you're calling dynamical degrees of freedom.
Yeah, that's right.
Okay.
So I should emphasize that in general relativity, in the full field theory, it is a field theory, so we only have fields in that theory. So the dynamical degrees of freedom are fields, and so the reference systems will be fields. Okay, so they generally you want to use if you're having a generic space-time. Since we have four-dimensional space-time, what we sort of need is essentially four independent fields to locally parameterize the space-time. So essentially three fields to parameterize spatial directions and one field to parameterize temporal directions. So there exist many such models where you can do that. Yeah. Okay, so that's for the full field theory. And in cosmology, because cosmology, these are symmetry-reduced models. They're not field theories. They're just mechanical systems, if you want. And there, okay, you get these really simple examples. So, but indeed, you should not think in full general relativity of these reference degrees of freedom as being really localized degrees of freedom necessarily. Okay, so I mean, there can be really global degrees of freedom. Okay. So Karel Kukash termed this problem that a priori in general relativity you don't have any specific choice of, or there's no unambiguous choice of what is a good clock variable in your theory. And if they give different quantum theories in the end, so he called the multiple choice problem as one of an embarrassment of riches. Out of many inequivalent options, one does not know which one to select. Isham made the following quote, then can these different quantum theories, so the different quantum theories you get from different choices, can they be seen to be part of an overall scheme that is covariant? And then he also said it seems most unlikely that a single Hilbert space can be used for all possible choices of an internal time function. So the internal time function is the dynamical clock degree of freedom that you've chosen. And indeed, he was quite right. And some of the work I've done that I want to explain is indeed to address this problem here, and indeed to show that these different theories can be part of a scheme that is actually covariant. And indeed, it will not just involve a single Hilbert space, but several Hilbert spaces. Okay, so so now the question is, okay, we have now different possible choices of reference systems, dynamical reference systems. And so if that's the case in the quantum, how can we actually make sense of the notion of general covariance when we take serious that frames are actually dynamical and quantum? Is there a way of developing a scheme that is a bit similar to the classical case, this idealized case where we have simple coordinate changes? So can we also have a scheme that allows us to systematically change from one quantum reference system to another? And so although this seems like a very important question for quantum gravity, so in quantum gravity, this active diffeomorphism invariance is a very big topic, but often this more operational notion of general covariance is actually sort of neglected. And so there's not actually so much work on this problem, although general covariance is, of course, a pillar of general relativity, and you would somehow want to make sense of what this would mean in a quantum regime. Okay, so there's a bunch of past literature on this. I will not really focus on these things. In fact, so some of this was done during my PhD, and you may also know Flaminia Giacomini. She was a visiting student here some 1.5 years ago, something like this. So I won't really talk about this stuff here. I will rather talk about some more recent work that's kind of, you can think of as being a synthesis of these previous works, and in some sense also converges some of the ideas coming from quantum foundations and quantum gravity. So and yeah, and the idea here is really to develop a quantum reference frame change method, and also to have such a compositional structure of perspective changes. Okay, before I go into this, let me briefly discuss something else, why you shouldn't be surprised that we can obtain such a compositional structure also for quantum reference frames. And this has something to do with very general properties in physics. So when we think of physics, we have some physical scenario or set of possible physical situations that we want to describe. And then we usually choose some kind of perspective that defines as a map from the physics we want to describe to some mathematical description. Okay? So more mathematically speaking, we can denote this by some set as phys. The description could be another set that is the mathematical description of the set of physical events that we want to describe. And the perspective is then really somehow a map that takes us from one to the other. So I will give you some examples. So for example, we can think of a bunch of billiard balls flying through space. That by itself, this could be a set of physical, one possibility of physical situation. And in order to, like I said, in order to make that statement, we don't have to specify any reference frame to make that statement that there's a bunch of balls flying through space. But if we want to say how fast they're flying through space, then we may want to choose some mathematical encoding of this. And for spatial velocities, of course, the R3 would be a very useful way of doing it. So that, of course, amounts to making a choice of a basis in the description in this case. So a choice of basis in R3. So we would map under some perspective map the spatial velocities in actual space into some vectors in R3. Now, so one thing that I'm trying to emphasize is that a priori these sets of physical scenarios or situations, that's something that you can consider as being perspective neutral. There's many different ways in which you can describe it. And you don't need to specify a frame in order to describe that. So we have that in general relativity as well, as I already tried to stress. So we have our space-time, space-time neighborhoods, and these images that I showed you before. You have some frame-independent physics there, and then you can choose some coordinate map that maps you into R4. That's a good mathematical description. But you also have it for quantum states, for instance. You can prepare some quantum states in the laboratory, let's say some spin system, and then you send it through a Stern-Gerlach magnet. But then, there's many different ways in which you would want to represent a particular quantum state. And of course, that amounts to choosing some basis in your set of density matrices, let's say. So there's of course many different ways in doing that. There's zillions of examples in physics, and often these perspectives are associated with some reference frame. So in the mathematical description, usually also with a choice of basis. And quite generally, if you want to go from one mathematical description, which we could consider description relative to some perspective, and we want to change perspective, well, then again, we have to sort of invert this map relative to one perspective, go back to the perspective neutral physics, and then map forward to the new perspective. So, and this always goes here, this concatenation here, this symbol in the middle signals that you're always going via the perspective neutral physics in the middle. So note that these phi's here are not necessarily coordinates maps on a manifold. They're just quite generally some descriptions that you use for for describing certain physical situations that you're interested in. And so this is something that we will now also see for quantum reference frames. So the question here is then, what is actually that perspective neutral structure? Okay. So let me briefly tell you the idea of how we do this. And then afterwards, I will illustrate this in an example system. So the aim here is, again, to develop a systematic method for switching quantum reference frame perspectives. We use some symmetry principle, just like we have it in generativity, for example. The symmetry principle usually leads to some redundancy in the description of physics. For instance, when you have gauge symmetry, then of course not all degrees of freedom are physically relevant. And this redundancy allows us to describe all physical degrees of freedom, or all degrees of freedom on an equal footing, including the ones that we want to choose as a reference system. And then we can always pick those degrees of freedom that we want to pick as the reference system, those we pick as the redundant ones, and then through some symmetry reduction or getting rid of redundant degrees of freedom, we then obtain a description relative to that set of reference degrees of freedom. And this allows us...
Can you give an example of a symmetry principle?
Yeah, so let me just do that in an example, a couple of slides. Actually, okay, time is running. So as a spoiler, let me just tell you what you roughly get. So you get some maps between Hilbert spaces where there exists something like a perspective neutral Hilbert space, which I will explain hopefully in a couple of minutes a bit better. And then you get something like quantum coordinate maps that are something like quantum symmetry reduction maps that take you from a larger Hilbert space to a smaller Hilbert space in the end. And it turns out that wherever these are invertible, you can basically map from one perspective, that's like a reduced quantum theory, to another reduced quantum theory, again by mapping via the perspective neutral physics. Let me illustrate this because I see that time is, I don't know until what time I've... Five-ish. Yeah. Let me try to illustrate this in a very simple model. Then this will become a little clearer. So also coming to your question, what I mean by a symmetry principle. So in generativity, it would be diffeomorphism symmetry. But here, of course, generativity is a bit difficult to treat explicitly, the full theory. So the simplest example that I can think of is the following. So we take three particles in one-dimensional Newtonian space. So these are my three collaborators on that one project. I model them as unit mass balls in 1D space. And so suppose we have now this Lagrangian given in this form. So we have the usual kinetic term, and then we just subtract the center of mass energy. And that's suppose the potential is translation invariant. It only depends on relative distances. Then it's very easy to convince yourself that this Lagrangian actually is invariant under global translations. So if you take your dynamic degrees of freedom and you just add some arbitrary function of time to that, then it doesn't change the Lagrangian. Okay, so it's in some sense a gauge symmetry if you want. Now, we can go to the canonical description. We can do a Legendre transformation. And what you will find is that, well, you get a Hamiltonian that looks like the usual form that you would expect, but then it gets an additional term here. And this additional term is something that is actually constrained. So it is a function, here in this case, it's just the sum of the three momenta of my collaborators. And so it's the total momentum, and you will find that it is constrained to vanish. It has to be zero. So what this actually means is this Legendre transformation, in contrast to the usual textbook scenarios in first year mechanics, is not actually an invertible map. It's not a surjective map from your space of velocities and positions to your phase space. And what you also see is that this total momentum is, of course, the total translation generator. So this is the canonical incarnation here of the gauge symmetry generator that comes from your Lagrangian picture. Right? In the Lagrangian picture, you have the global translation invariance, which you see by the invariance under these additions of arbitrary functions of time. So what does that actually mean? It means that the dynamics that you're describing relative to the Newtonian background space, that's not physically relevant. The only thing that is relevant is actually the relative motion between the different particles. And yeah, so the global gauge transformations, they're in the canonical formulation described by this constraint. So this is a generic feature that you will see in gauge theories, that in the canonical formulation, they will always lead to constraints. Now, now coming to this redundancy that I was talking about before, so because of that gauge symmetry, QA of t is not a physical degree of freedom by itself, because you can always, like I said, you can translate it, and then where it is in the background Newtonian space, that's not physically relevant. But of course, I can look at gauge invariant observables, and like I said, the relative motions of these three particles, that is of course invariant under global translations. So these are actually gauge invariant relative observables, if you want, and indeed, as phase-space functions, they commute with the generator of your global translations. Okay? Then you also have the momenta, of course, that also commute with the total momentum. So they're also, in fact, gauge invariant properties. So gauge invariant really, I mean, so the generator of translations in terms of Poisson brackets has an action on other phase-space functions. And gauge invariance means, or translation invariance means that that a function that the Poisson bracket of a translation invariant function vanishes with the total momentum. So in here you can think of this as being a very simple example of a perspective neutral description. It's like a description of the simple system prior to having chosen a reference system from which you want to describe the dynamics. So here we could pick any of the three of my three collaborators as a reference system, if you like. And we have a redundancy here because, of course, you see that the three gauge invariant relative distances are, of course, algebraically related. This one is just the difference between the first two. And of course, these are also not independent because this guy has to vanish. So, but which of these guys we consider as redundant, that's up to us. It's a choice we have to make. It's not what the system prescribes to us. And so this is why you can, this simple example, consider this as a description of the physics here prior to having chosen a frame. Okay, let me maybe skip this here. But in this case, we can take a perspective here by making an additional choice because we have a gauge symmetry involved. We can just fix that gauge symmetry, so it's like a gauge fixing condition. We can take Augustin's perspective, and we can do that by just setting QA, which is by itself not a physical variable, to be 0. So we define Augustin to be the origin in our system, and then we only look at how the other balls evolve relative to that origin. It turns out to be dynamically consistent, and when you do that, then these gauge invariant observables, well, they just become directly the distances relative to A. So we can just consider this as being the description of Esteban's and Flaminia's dynamics relative to Augustin's perspective. Okay, let me not go into this. The Hamiltonian also changes under this choice, but I don't think I have time to discuss this. Let me rather explain what this means now in the quantum theory and give you an illustration of these quantum reference frame switches in this very simple example. So if we want to quantize the system now, again, we have these three balls, and so they live in a one-dimensional Newtonian space. So the configuration space is just three-dimensional, and we pick as a Hilbert space for quantizing the system simply an L2 over R3 to start out with. And then what we want to do is we want to solve that constraint that we have, which we can now quantize. We want to solve that constraint in the quantum theory. So we impose it as an operator condition on the states. And then we only consider those states as physical, which are annihilated by that constraint. And this is so-called Dirac quantization. Now, that leads to some projection from, in fact, this kinematical Hilbert space to some physical Hilbert space, the space of solutions to that equation, which I'm not going to describe in detail here, but in practice, roughly what you can do is you can take some kinematical state, expand it in the momentum basis, depending still on all three momenta, and then you can solve that constraint. And of course, it's very easy to convince yourself that one way of solving it is simply by writing a physical state in this form, just by solving, for instance, PA in terms of PE and PF and just inserting it here. So it's very easy to see that that solves that constraint here. But of course, you see that there's now again a redundancy because I could also solve for PE or PF. And then that gives me different ways of writing the same physical state. So I can write the same physical state in many different ways. And that will be related to, again, the choice of quantum reference frame here in this very simple example. Now, you can also ask, what are now the gauge invariant observables here? Well, they should live on the space of solutions, but if they are supposed to live on the space of solutions, they better be invariant under the action of that constraint. So they have to commute with the constraint, for otherwise they would map out of that space of solutions. And here it's very simple. They're just the quantizations of these relative observables that I already showed you classically. And here, so you have now a redundancy both in the description of states, but also in the description of the quantum degrees of freedom. So because again, of course, they're algebraically related. Yeah, algebraically related. So, and now we want to exploit that redundancy in order to go from this description that we have here, which we again interpret as a perspective neutral description, as a description of the physics of these three balls prior to having chosen a reference system. And yeah, removing that redundancy, we want to relate to a choice of quantum reference frame here. So in contrast to the classical case, there's no gauge fixing here because the quantum theory is already gauge invariant on the physical Hilbert space because the constraints act trivially there. But let me not discuss that further because there's not so much time. Let me just illustrate in this example how you would now reduce the theory to go to something that we may interpret as a quantum frame perspective. So we start out again from the perspective neutral physical Hilbert space, and then we choose some reference system. Let's say we pick Augustin again. And then the second step is something where we transform the constraints in such a way that we transform the entire redundancy that we have in our description of the system only into the reference frame degree of freedom. So we thereby fix the reference frame degree of freedom through the constraint, and then we have a way of getting rid of it afterwards. So here, to illustrate this, we can define a map that we can call a trivialization that changes the constraint, which depended on all three degrees of freedom, and after transforming it, it only depends on our reference frame degree of freedom. And when we do that and also transform our physical states, then the physical states, they factorize, so they become, if you want, a product state, where the reference frame part of the state is completely redundant. It doesn't carry any more information about the original physical state, and all the relevant physical information is contained in the rest of the state. Okay, so and in the rest of the state, you can now really interpret as a description of Esteban and Flaminia's physics relative to the frame A. It only depends on the degrees of freedom of E and F. And what we want to do is now get rid of the redundancy. We can do this by projecting onto the classical gauge fixing conditions here. In this case, the projection on the classical gauge fixing condition is just projecting on QA equals 0. This is what we did also classically, setting QA equals 0 to go to Augustin's perspective. If you do this, well, then you're just, you concatenate this, and then what you're left with, acting with, these maps together on the physical state in the end, well, then you get a state, a reduced state, where there's no longer any redundancy in it, and which has no more dependence on the reference frame degrees of freedom, and you can consider that as being the description of the remaining physics relative to that frame. Now, it also turns out that the observables actually transform correctly under this map here, this symmetry reduction map. So the relative observables, they transform exactly into the distances relative to A, and well, the momenta transform trivially. And it also turns out that the total Hamiltonian transformed in the correct way, in which one would expect it. This here is just the quantization of what I gave you before of this reduced Hamiltonian. So what we get here is that in some sense states transform correctly, observables transform correctly. We have an isometry, and the dynamics transforms correctly, and there's no more redundancy here. And so we can interpret this here as a description of Esteban and Flaminia's motions relative to Augustin's perspective. Now, let me briefly describe how you would now switch frame perspective in the quantum theory. So what I've shown you is how to go from the perspective neutral physics via these maps that I just showed you to a Hilbert space where there's no more redundancy and where the reference frame degrees of freedom are no longer living on it. And of course, you could have done the same thing relative to a different reference frame choice, let's say Flaminius perspective in this case. And it turns out that these maps are actually invertible. Okay? So you could also invert these guys. But let's say we want to go from Flaminius perspective to Augustin's perspective. Well, we can invert these maps that I showed you. That's like the inverse coordinate map, quantum coordinate map, takes you from Flaminius perspective through the perspective neutral structure into the perspective relative to A's reference frame. And if you do that, actually, so it has this compositional structure. You can spell out these maps, and they look a bit horrible in this form. They simplify tremendously, and it turns out that when you do this, you reproduce a quantum reference frame transformation that actually has been proposed before by my collaborators in a completely different way. So it was more an operational perspective. They didn't use any symmetry principle, no perspective neutral description like I'm describing it here. And so you can see here, the nice thing about it is that these transformations that they proposed, we can now derive them from first principles, so from first symmetry principles if you want. Of course, this is an extremely simple system here, but this method turns out to work much more generally. So one thing I want to emphasize here is what kind of operational consequences such maps actually have. And it's easy to get lost in these mathematical details, but it also has some cute implications. So this stuff here I have not been involved in. This was done by Flaminia mostly. So this is from their previous paper. What they showed there is that these maps that we recovered here, so there's some funny things happening. So here they label the systems A, B, C, not A, E, F, like me. But suppose now we're now in some C's perspective, and C is viewing A and B to be in an entangled state. Then it turns out that if you apply this quantum reference frame transformation that I showed you on the previous slide that I derived there to this description, so this would be a reduced state, and then you map to A's perspective, what you actually find is that in that case, C and B turn out to be in a product state, and B will be sharply localized relative to A, while C will become delocalized. So one thing that this implies is in some sense that superpositions and also correlations actually become quantum frame dependent.
This is well known in other contexts, however, that entanglement is tied to the choice of tensor product decomposition. So the same state.
But this is not the same as this here. So I mean, this here is a very. So I mean, this here is really. I mean, the structure using constrained systems is quite different than what is usually done in the quantum reference frame literature. So are you talking about the? Well, I guess you're talking about the usual description in quantum information, like in finite dimensional systems and so on. Is that?
Well, you mentioned entanglement, so yeah. I assumed you made reference to the standard notion of entanglement, sure. Yes, which is a linear combination of sure. Product states in composite systems. So the problematic notion can be subsystems because. Yes, that's true. But so the thing is that these reduction maps that we use here, so they're quite different from the reduction maps you have in that you usually use in quantum mechanics when you go to reduced states, like tracing out degrees of freedom. This is very different from that, actually. Yeah, all I was saying is that the concept of entanglement, the fact that it changes depending on perspectives, is something that.
Yeah, no, I mean, sure. I mean, so there have been works before that showed this in other contexts that may be true. But this year, the way this happens here, I do think is different than in those other contexts.
Are there any actual differences in predictions?
Right.
In predictions to the other examples, you mean, right?
You're saying that these are distinct ways of arriving at something that looks similar. Are there any places where they disagree?
Yeah.
okay, I don't know. So, but the thing is that here, I mean, the way these descriptions are done here, I mean, I think they're quite different than in these other cases, because in the other cases you don't really describe the other degrees of freedom from a quantum system itself, and so this is quite different here. So the degrees of freedom that we have here, they come really from a superior quantum theory. So the reference frame degrees of freedom are really quantum itself. And I don't think that's the same as in these other. So I wouldn't even know at this point how to exactly relate those.
Well, it's hard to answer because I don't know what experiments you're thinking.
Well, I mean, this is of course here one-dimensional examples. That's a bit hard to test experimentally,
right.
but I wouldn't even. So technically, I don't think there's much relation to the other descriptions. Okay. Yeah. Anyway, so maybe in these other descriptions you have something that seems, conceptually, or not conceptually, but qualitatively similar. But I think here, conceptually and technically, it is different.
So for example, a photodetector that's center of mass is in the superposition of two positions, for example, is one of the elements.
Sorry, it's one of the elements.
All based on the idea of three particles in a 1D simplified universe. So it could well be that the standard predictions of what would happen when you change, maybe you don't need to assume something about this concept of changing reference frames to get the same sorts of predictions about changes in the picture of entanglement, possibly for this system. Mm-hmm. I'm interested to know, is there more predictive power if you invoke what you're calling a more powerful framework?
Yeah, so I mean here, I mean it's a bit hard to say at this point because it's still this program is in its infancy. So this works much more generally than this very simple example that I've given here. But to really apply it to more realistic scenarios is a bit hard at this point. But I would still say conceptually and technically it is quite different in the sense that here we're really considering the reference frame degrees of freedom as properly quantum. Okay, so I mean we have this perspective neutral description, and they're all degrees of freedom A, B, C. They're all quantum degrees of freedom. Now we apply some quantum coordinate map if you want that removes any redundancy in the description, and then okay, you're left with the remaining degrees of freedom other than those of your reference frame. And I don't think that's what's usually done in quantum information, because there you still work somehow with lab frames, classical lab frames in some sense, and this is not what we do here.
But if you can predict the same results without having to actually invoke anything about quantization of reference frames, then...
Sure, but I doubt that this will be the case, to be honest.
That's the question.
Sure. She also mentioned when you're talking about changing partitions and changing things from being entangled or not, here it's those Hilbert spaces, in some sense, the joint Hilbert space describes the same two systems. It's just you're partitioning in different ways. Here, it's really the Hilbert space is describing a different physical system in some sense. When you change these perspectives, I don't know if that.
Yeah. So I mean, the thing is that of course here in the so here you didn't describe A and B. These are two dynamical degrees of freedom relative to some reference frame C, and here it's C and B that are dynamical. So it's really different.
They changed the reduction maps to different subspaces.
So just thinking of the physical, looking to the future, looking at a physical example. So C could be the cavity reference frames.
C could be, yeah.
And then A could be a photodetector within the cavity, and then B the internal degree of freedom. But the idea here is that you're treating the cavity itself at its center of mass quantum mechanically, which we don't usually do, but it could be a quantum system. And then you're just going from the cavity frame to the center of mass of the detector's frame, and but each is quantum degree of freedom. So you're developing a formalism that allows us to start to think about these situations, which we don't normally do.
Exactly. So I mean, the thing is that I would think, I mean, maybe in some limits you would recover what has been done before, when the reference frame degree of freedom that you're using is maybe very classical or something like this, and then the rest will behave as in usual considerations. But I think this is probably more general in the sense that here you can also look at arbitrarily quantum reference frames that are in totally, in very non-classical states. So So I think there's quite some difference. But anyway, I think time is running out. Of course, I didn't get anywhere nearly where I wanted to go to. But yeah, let me just emphasize that. So this can be extended to more complicated scenarios. For instance, the 3D relational n-body problem. There it turns out to be way more complicated, and that has to do with basically a rotation group. You cannot do any global gauge fixing. You can interpret that as, in some sense, the quantum reference frame perspectives not being globally valid in some sense, a bit similar to how coordinate descriptions on a manifold are not always globally valid. And then one can also apply this, in fact, to quantum clocks or in the problem of time. I don't think I will have time to discuss this now. And in particular, you can address that problem that I was mentioning before, the so-called multiple choice problem of time. You can actually map now between different time evolutions or time evolutions relative to different dynamical clock degrees of freedom, also in relativistic systems. That's what I looked at last year. And that's also something that we're currently looking at with Alex. There's hopefully another paper coming out very soon. But in all these cases, the reduction map is actually, this quantum symmetry reduction or quantum coordinate map is the same. You have to choose somehow your degree of freedom that you consider as redundant. So you always associate the redundancy or pick as the redundant degrees of freedom those that you want to use as reference frames. Then you transfer the redundancy to that reference frame degree of freedom, and then you remove the redundancy by projecting onto some state of the reference frame degree of freedom. And in all these examples, what you get is really quantum frame changes that take this compositional structure of quantum coordinate changes. If you want, you have your larger Hilbert space. It's this physical Hilbert space, which you can consider as your perspective neutral Hilbert space. And then you have the reduced descriptions relative to the reference frames. And you can map between them using these quantum coordinate maps. Okay, I think I should probably just conclude so far. I ran over time heavily, so yeah, let me just maybe finish here. And
Maybe we can continue next week.
I mean, if you guys are interested, I can also just.
People come back.
We
So-
love clocks.
Yeah.
Sorry?
We all love clocks.
Yeah, so then. So yeah, the second part would be clocks, but.
Let's do that. Let's continue. Find a time, probably the same time, unless it's taken. We can just why don't we do that? And then we don't have to rush and go crazy.
Yeah, no, well, I mean, I would have ended now anyway because I'm, of course, heavily over time. Yeah, the beginning, I thought I'd include some more general discussions that, because I don't know what the backgrounds here are. But in the end, I guess.
Very good.
I guess in the end, I had to break many of my promises from my abstract, many things I couldn't do. But
Okay.
yeah, anyway, I think then I stop here. I won't keep you longer. Upshot here is, okay, there's a quantum frame change method, and one can apply it to many different things.
Thank you.